Hello everyone, welcome back to your physics class. I'm Mr. Idris, physics teacher, and I'm so happy to be here to help you and to explore the whole chapters of physics for grade 12 students. And before we dive into the new lesson, I would like to quickly recap to the previous lesson and what we have learned in the previous lesson. If you remember, in the previous lesson, we studied that how can you determine the magnetic force on a charged particle. When a charged particle is moving into the magnetic field, this magnetic field exerts a magnetic force on this charged particle. So the charged particle becomes the charged particle has maximum magnetic force when it's moving perpendicular to the magnetic field. So in today's lesson, we are focusing on the magnetic force, the second type of the magnetic force, on the current carrying conductor. Okay. In a previous lesson, we studied the magnetic force on a charged particle, but in this lesson, you will learn how can you determine the direction and the magnitude of the magnetic force on a current carrying conductor. For example, when the current carrying or passing when the current passing into the conductor, so this into the magnetic field, and this wire is already placed into the magnetic field. This magnetic field exerts a magnetic force on this wire, and in this, by using this equation, you can determine the magnitude of the magnetic force on the current carrying conductor is equal to B I L sine theta. Okay, so in this way you can determine the direction, the magnitude of the magnetic force on a current carrying conductor. So how about the direction? How can you determine the direction of the magnetic force on a current carrying wire? By using right hand rule. But here we don't have palm. Okay, we don't have here. We have only out of palm. The thumb is represent for the direction of the current, and the four fingers, as usual, is the direction of the magnetic field. And here only we have one force. The force of the wire is here, okay, in positive. If you remember, for the charged particle, we have two forces, positive force and negative force. But here, for the current carrying wire, only we have this force, okay? As you can see in this figure, guys, look. The direction of the magnetic field is directed into the page. So this is field. And the direction of the current carrying into this wire is upward here. Okay, upward. The direction of the magnetic force, it should be directed to the left. How? By using right hand rule. Where is the direction of the current? Upward. Where is field? Into the page. And here is already becomes what? The direction of the magnetic force. So here the magnetic force is directed to the left. What does magnetic force on a current carrying conductor depend on? According to its equation, depend on the magnetic field, the amount of the current, length of the wire, and angle between what? Sorry, B and I. Angle between what? B and I. If this angle is parallel, magnetic force becomes 0. If the angle between B and I is 90 degree or 270 or perpendicular, the magnetic force becomes maximum. And if the angle between B and I is 30 or 150, the magnetic force becomes half of its maximum value. So when does magnetic force on a current carrying conductor become maximum value? If the angle between I and B is 90 degree or perpendicular. When does the magnetic force become 0? If the direction of the current and the magnetic field is parallel, 0 or 180. So when does magnetic force become half of its maximum value? If the angle between B and I is 30 degree or 150 degrees. Okay, I mentioned here all the situations. So the direction of the magnetic force, guys, always perpendicular to the direction of the current. And the direction of the magnetic force is always perpendicular to the direction of the magnetic field. This is constant. But the angle between B and I, it varies, it changes, it depends on the question. The applications of the magnetic force on a current carrying wire, okay? The applications of the magnetic force on a current carrying wire, now I'm going to explain in detail. So this is very important. What is loudspeaker? Guys, loudspeaker, in a loudspeaker, when the direction of the direction and the magnet of the current in the coil of wire change, the paper cone attached to the coil moves and producing the sound waves. how the loudspeakers work. So the loudspeaker principle based on the magnetic force on a current carrying conductor. So this loudspeaker is working because of the magnetic force acting on the coil of wire, and the variation of the magnetic force on the coil of wire, it goes to vibrating the attached paper cone of the loudspeaker, and it produces a sound wave and the amplified sound wave. Guys, now I'm going to explain in detail how the loudspeaker work. Okay, but before loudspeaker, I would like to explain the microphone. In a speaker system, a sound signal, guys, look, sound signal is converted to what? Electrical signal. By what? By microphone. By what? By microphone. Sound signal is converted to a varying electrical signal. By what? By microphone. So what is the function of the microphone? Convert sound signal into a varying of electrical signal. The electrical signal is amplified and sent to the loudspeaker. So this electrical signal is sent to the loudspeaker. This varying electrical current, the variation of the electrical current that induced by the microphone causes a varying magnetic force, causes the change of the magnetic force. Why? Because the direction of the magnetic force depends on the direction of the current. When the direction of the current changes, the direction of the magnetic force also changes. Okay, so that is why the variation of the electric current, it goes to the variation of the magnetic force on the coil. So this alternating force on the coil results in the vibrations of the attached cone, this paper cone, which produces a vibrations in the density of the air in the front of it. So in this way, the loudspeaker works. We have a short video about the loudspeaker and how the microphone and the loudspeaker works. Okay, listen and watch attentively, please. Look at this video. Is about how loudspeaker and how microphone works. Listen carefully, please.
Moving coil microphone. Microphone is an instrument which can convert sound signals to electrical signals continuously. Today, different types of
Guys, this is microphone, convert sound signal into electrical or into the varying of electrical signal.
Microphones are in use. They work under different theories. Here we are going to study about moving coil microphone.
This is microphone, and look what we have inside the microphone.
Voice coil is an important part.
So this is the voice coil. We have a very thin coil inside the microphone. So this very thin coil is vibrating or moving when like for example, when the compression of the sound is heated this coil is vibrating or moving into this magnetic field. In chapter 6 we will study the Faraday inducing current by moving a conductor or a coil of wire into the magnetic field. When there is a relative motion between the wire and the magnetic field, the current is induced. So the induced current is AC current or alternating current. Okay, so it is direction and magnitude changes continuously. When the sound is, like for example, enters this voice coil and the coil is very thin and is vibrating, the vibration of the coil into the magnetic field induces a current. So that is why microphone convert sound signal into electrical signal. Let's go on.
Microphone. And it is a coil of very thin insulated wire.
Very thin insulated wire.
The voice coil is designed such that
this is magnetic field. Magnetic field.
Poles of a magnet. This coil is connected to a diaphragm. Let's see how the microphone converts sound signal.
So when the coil is vibrating into the magnetic field,
is designed such that it can vibrate freely in between the poles of the magnet. This coil is connected to a diaphragm. Let's see how the microphone converts sound signals into electrical signals.
This
The
is
diaphragm
sound signal
vibrates with sound
enters
signals
the,
incident on it.
and
The
it
voice
goes
coil
to
also
move, vibrates
vibrates
the
in
voice
accordance with the
coil
diaphragm.
and induces current.
These vibrations cut the flux lines.
This is sound signal enters the voice coil, and the voice coil also vibrates, okay? And the vibration of the voice coil into the magnetic field induces an alternating current. So in this way, the sound wave converted to electrical wave or electrical signal by microphone.
And thus electrical signals are induced in the voice coil.
Electrical signal, and this is sound
These
signal.
signals are strengthened by using an amplifier and sent to a loudspeaker. Moving coil
Now,
loudspeaker.
Is about the loudspeaker, how the loudspeaker works.
Moving coil loudspeaker.
So the permanent and the components, the components of the loudspeaker.
The important part of the loudspeaker is permanent.
This is the parts of the loudspeaker. We have a permanent magnet, voice coil, and diaphragm. And this is the paper cone.
The voice coil is placed between the opposite poles of
the voice coil is placed into the magnetic field, okay, the permanent magnetic field.
Or a diaphragm is attached to the coil. The electrical signals corresponding to the
guys, this electrical signal, it is the induced current of the microphone, okay? So this is the induced current of the microphone when it is converted by the sound wave. So this induced current sends from the microphone to the loudspeaker. This current produces a magnetic force into this coil of wire, because we have a magnetic field B and we have current I, and also we have the length of the voice coil and the wire. So in this case, the magnetic force acting on this paper cone when attached to the loudspeaker, and because the current is AC current, alternating current, so that is why the magnetic force also changes continuously. And this changing of the direction of the magnetic force continuously, it goes to vibrating the paper cone, and as a result, it produces the amplified sound. Look. And again, the electrical sound is converted to this sound wave finally. Why the voice coil is vibrating? Because the magnetic force changes. Okay?
In accordance with the intensities of the electrical signals.
So this vibration of the voice coil is resulted from the magnetic force, and this magnetic force is resulted from the induced current when carrying into this coil into the magnetic field. So this is the basic and the principle of the loudspeaker, that based on the magnetic force on a current carrying wire. Let's go back to our topics and our pamphlet. Look. Look at me. What's wrong here? Okay. On what physical principles does a loudspeaker operate? It depends on the magnetic force acting on a current carrying wire in a magnetic field. What function does a microphone perform in a loudspeaker system? Converts sound signal into or to electrical signal. Sound signal is converted to electrical signal by microphone. So what are the main components of the loudspeaker? We have three main components and parts of the loudspeaker: a permanent magnet, a coil of wire, and a flexible paper cone attached to the coil that acts as the speaker. What role do the magnet plays in the loudspeaker? Using magnet in a loudspeaker is essential for creating a magnetic field. Without magnetic field, the force does not exist in the moving coil. What role does the paper cone plays in this design of the loudspeaker? The cone amplifies and projects the sound waves into the air. And now we have another topic. The magnetic two parallel conducting wire exert force on one another. If you have two parallel wires, these two parallel wires, and one current carrying into these two wires, and these two wires exert force on one another. Okay, the first wire exert a force on the second wire. Okay, so now, for example, assume that we have two wires and the current runs in these two wires. So when the current runs in the same direction, and the force between these two wires becomes attraction force. But when the current runs in opposite direction, the force becomes repulsion force, and I'm going to explain in detail. In this case, when two parallel wire places side by side, okay, like as you can see, like for example, these two conducting wire, current runs in these two wires. The magnetic field for the first wire exert the magnetic force on the second wire, and the magnetic field of the second wire exerts a force on the wire of the first wire. Assume that we have two wires, guys. Look. Okay, so how many wires do you have? Two. This is wire 1 and this is wire 2. If the current runs in the same direction, upward, current runs in the same direction. So do we have force between these two wires? Yes. Do we have force between these two wires? Yes. What is the force between these two wires? Attraction force or repulsion force? Now I'm going to tell you. According to the right hand rule, if you remember in chapter 5, Oersted, magnetism from electricity, when the current carrying into the straight wire, the thumb is the direction of the current and the four fingers curls in the direction of the magnetic field, and the form of the magnetic field is concentric circle. How can you determine the direction of the magnetic field for this wire? By using right hand rule. Here is into the page and here is out of the page. Okay, for wire number 1, here is into the page, here is into the page. This is for B1, and here this side becomes out of the page. Here becomes what? Out of the page. Okay, so this is B1. This is what? This is B1, the magnetic field on the first wire. For the second wire, wire number 2, this is I1, this is I2. This is L1, this is L2. For the second wire, use the same rule, the right hand rule. Here is becomes into the page and here is out of the page. Okay, here becomes what? Into the page. And here is out of the page. Okay, guys, look, what is the force between these two wires? The force between these two wires becomes what? Attraction force or repulsion force. Here, how many fields do we have, guys? How many fields do we have? 2 fields. B1 into the page and B2, this is B2 out, B1 out of the page, B2 into the page. Okay, how many fields do we have? 2 opposite fields. Like north and south, the opposite poles attract or repel. Absolutely, they attract each other. Okay, because how many fields do we have? 2 fields, B1 and B2. Sorry, because we have 2 different fields. That is why the force between these 2 wires becomes what? Attraction force. Like north and south, attract or repel? Attract. But how about north and north? Of course, they repel each other. Okay, but here, force F1 is directed to the right, and so F2 directed to the right, but F1 is directed to the left. Okay, so the force between them becomes what? Attraction force. But guys, be careful. F2 resulted from what? From B1. The magnetic field of the first wire exert and produce the magnetic force for the second wire. Why? Because without magnetic field, the force does not exist in the wire. And the magnetic field of the wire does not exert a magnetic force. Like, for example, if you have a wire, look. So this is wire, okay? When the current carrying into this wire, I, okay? Do we have length? Yes. Do we have current? Yes. Do we have field? No, we don't have field. but this field is the field of the current. The field of the current, this field does not exert a magnetic force. Only there should be an external magnetic field to exert a magnetic force on the wire. So here, magnetic force is equal to what? BIL. Do we have L? Yes. Do we have I? Yes. But we don't have B here. The magnetic field that created by its own current does not exert magnetic force on the wire. Keep in your mind. So this is very important, guys. Don't be confused, please. So that is why the magnetic force on the second wire exerted by B1 and the magnetic force of the first wire created by B2. Okay? So how can you write the equation for both magnetic force, F1 and F2? Guys, look. This is F1 and this is F2. F1 resulted from what? From B1. It becomes B2, I1, L1. How about F2? F2 is resulted from B1. Okay? B1 becomes external field for F2. And B2 becomes external field for I1. B1, I2, L2. So in this way, you can determine the force for each of the wire. So if the current runs in the same direction, the force always becomes attraction force. Yes, of course. How about if the current runs in opposite direction? Now I'm going to tell you, it becomes repulsion force. How? Look. This is the two parallel wires. Okay. The current runs in opposite direction. Current runs in what? In opposite direction. Here is downward and here is upward. How many wires do we have? Two. The two wires placed parallel to each other, yes. And the current runs in the same direction or opposite direction? In opposite direction, okay? When the current runs in opposite direction, so what will be the force between these two parallel wire? The force, it should be repulsion force. Why? Now we're going to explain. According right hand rule, this is wire number 1 and this is wire number 2. This is L1 and this is L2. Okay? This is I1, this is I2. I1 is downward. Here becomes what? Into the page. Here is what? Into the page. Okay, so what is this? This is B1. And here becomes what? Out of the page. Into the page, out of the page. So how about wire number 2? In wire number 2, according to the right hand rule, here becomes what? Into the page. Here is what? Into the page. This is B2 or B1. This is B2. Created by what? By I2. B1 created by I1. B2 created by I2. This is B2. Okay? And if here is into the page, this side becomes out of the page. Out of the page. Okay? So guys, look. How many poles, how many fields do we have here? We have two fields, B1 and B2. These two fields are in the same direction or opposite direction? In the same direction, like north and north. North, north, south, south, same field, same pole, attract or repel? Absolutely, they repel each other. So that is why the force between these two wires becomes repulsion force. Okay? F1 is directed to the, F2 directed to the left, and F1 is directed to the right. So in this way, you can determine the attraction and repulsion force between two parallel wires when the current runs in these two wires. The force becomes what? Repulsion force. Okay? And here we have some notes. Current carrying in a conductor creates its own magnetic field. I1 creates B1, I2 creates B2. But F1 created by B2 and F2 created by B1. So when two current carrying wire are placed close together, they exert magnetic force on each other. When the two conductors are parallel to each other, the direction of the magnetic field, guys, look, listen carefully, the direction of the magnetic field of one wire, like for example, B1 is perpendicular to I2. So how about B2? Is perpendicular to I1? Yes. The direction of the magnetic field of one wire is perpendicular to the direction of the current of the second wire. Okay? And the current carrying through the first wire creates B1 and A2 creates B2. Force is equal to BIL. The amount of magnetic force on the first wire, F1, produced by what? By B2. But F2 created by B1. And if the direction is parallel between I and B, the magnetic force becomes 0. If the current in the same direction current between two wires, force attraction. But opposite direction between two wires, force becomes repulsion. These two questions, why current in the same direction, they becomes attraction force. I explain it, as you can see in this figure, because of the fields. Question 14 is the same of these two questions. Explain why two parallel wire carrying in opposite direction repel each other. As you can see in this figure, why the force is repulsion between these two parallel wires? Because the direction of the magnetic field of one wire is perpendicular to the direction of the current of the other wire. The magnetic field from one wire, like B1, perpendicular to the second wire, to I2. The magnetic force on the second wire is away from the first wire. Question 18, guys, look at question 18. We have a stream of electrons. Guys, be careful. The direction of electron is always in opposite direction of the current. When the electron, like the stream of the electron is projected to the left, it means that the current is to the right. So when the electron is projected to the right, electron is directed to the left. Look at this question, question 18. A stream of electrons is projected horizontally to where? To right. This is question 18. The electron is projected to the right. This is the movement of electron. At the same time, when the electron is moving to the right, how about the current? Current is directed to where? To the right, to the left. Current is directed to where? To the left. Okay? Why? Because current, the flow of the electron is directed to the right. A straight conductor current is supported parallel to and above the electron. We have a straight conductor above the electrons. We have a current carrying in the conductor above this stream of electrons. We have two branches here. What is the effect on the electron stream if the current in the conductor, this is conductor, and this is stream of electron. Electrons. If the current in the conductor is left to right. Current left to right. This is left and this is right. From left to right, it means that the current is moved into the right direction. Current directed to the right. Okay? If the two, now how many currents do we have? Two currents. How many currents do we have? Two. The current of the conductor is directed to the right and the current of the electron to the left. These two currents, same direction or opposite direction? Opposite direction. If the current opposite direction, they repel or attract? Absolutely, they repel each other. So that is why the stream of electron is moving away from the conductor. Moves away from the conductor. Because these two current in opposite direction, so that is why the stream of the electron moves away from the conductor. Branch B, assume that when the current is reversed in the conductor, when the current is reversed, okay, it means that the direction of the current is directed to the left. When the current is reversed, it means that the direction of the current is directed to the left. How many currents do we have? Two. These two currents are in the same direction? Yes, of course. So that is why the force between them becomes attraction force, and the stream of electron is moving toward the conductor, or the stream moves toward the wire, the conductor. Okay, in the second part, the electron moves toward, because the force between the electron stream and the conductor becomes attraction force. Guys, question 19 related with question 18. Okay, the question says, if the conductor in item 18 is replaced by a magnetic field, replaced by what? A magnet with a downward magnetic field. Guys, this downward, it means Y negative or Z negative. So many students are struggling or confusing with this downward. So when does the downward is negative, and when does this downward the negative Y, and when does this downward is negative Z? Now I'm going to explain in detail and listen attentively, please. Downward. When does this downward is Y negative, and when does this downward is Z negative? This downward is Y negative if in the question right, we have right or left. If the right and left are mentioned in the question, or one of them is mentioned in the question, the downward, it means that Y negative. But if instead right and left, we have like east, west, south, north. If we have east, west, south, and north, downward, it means Y negative. Question 19 related with question 18. Guys, in question 18, the direction of the electron is projected to where? To right or to east? To right. So what we have here, right or east? We have right. So when the right, when you see the right in the question, downward, it means what? Y negative. So it means that the question in question 19, the direction of the magnetic field is downward. This downward is Y negative or Z negative? Absolutely is Y negative. Okay. So the conductor replaced it by a magnetic field. So the magnetic field is directed downward. Downward here is Y negative because we have left in the question. And the stream of the electron still directed to the right. So what will be the direction of the magnetic force? What is the effect on the electron stream? What is the effect on the electron stream and the force of the electron? The electrons moving toward the observer. Why? Because according the right hand rule, what is the type of the charge? Electron. The type of charge is what? Electron. So to find the direction of the magnetic force on the charged particle electron, so we have to use the palm of your hand. Okay, here. Okay, this is the direction of the velocity of the charge here to the right, and field is down, Y negative. Okay, where is magnetic force? Out of the page, toward the observer. Toward what? Out of the page, toward the observers. This is question 19. Question 20. Two wires carrying equal but opposite current. How many wires do we have? Two wires carrying equal but opposite current direction. Okay, equal in magnitude but opposite in direction. Twisted, as you can see in this figure. The two wires twisted together because the area of the first coil is not equal to the area of the second coil. So that is why the total magnetic field can never be zero at the middle of the two coils. But in this technique, the magnetic field reduces. So why does the technique reduce the strength of the magnetic field? Because the two currents are in opposite direction and they cancel each other. So that is why the total magnetic field decreases. Guys, look at the question about the magnetic force. Question, sample problem 5E. It's very easy. A wire 36 meters long. This is the length of the wire. 36 meters, carries a current I, 22 ampere, from east to west. From east to west, the current is directed to west. If the magnetic force on the wire due to the Earth's magnetic field downward, if the magnetic force is downward, so it means this is the direction of the current. Current to the east, sorry, to the west. The direction of the current is directed to the west. This is current to the west. And force is downward. It is magnitude 4 times 10 power negative 2 Newton. Okay? Guys, this downward force, it means that y negative or z negative and y. This downward in this case is z negative, not y negative. Why? Because we have east and west in the question. Do we have right and left? No. Do we have east and west? Yes. If we have east and west in the question, this downward y negative or z negative, this downward z negative if we have east and west. That's all. Okay? Be careful. So the magnetic force downward, it means that into the page. If magnetic force is into the page, okay, this is the direction of the force for the current carrying conductor into the page. Where is the direction of the current? West. Where is my fingers? North. Because the question asked it and was given by west, so that is why you have to answer by the north. Magnetic field is directed to where? To the north, sorry. Not y, to the north. To the north. How about the magnet? The magnitude of magnetic field is equal to what? The magnitude of magnetic field is equal to, guys, look. Magnetic force, B-I-L. How about B? Force over I-L. Do we have force? Yes. Do we have I? Of course. Do we have L? 36. You can replace and you can find the magnitude and direction of the magnetic field, which is equal to 5 times 10 power negative 5 Tesla. Question 1 in practice 5E. Question 1 in practice 5E. A 6-meter wire carries a current 7 ampere. L 6 meter. Current 7 ampere toward X. X is positive. The direction of the current is X is positive. This is the direction of the current. Okay? A magnetic force 7 times 10 power negative 6 Newton. Magnetic force 7 times 10 power negative 6 Newton. In which direction? Acts on in the Y direction. This is force. Y negative. Negative Y direction. Find the magnitude and direction of the magnetic field. B is unknown. At first, let's find the direction of the magnetic field. Where is magnetic force? Y negative. Where is current? X positive. How about magnetic field? Outward. Z positive. Okay? The direction of the magnetic field is directed into this Z positive. Okay? This is magnetic field Z positive. It is magnetic because magnetic force is equal to BIL. Rearrange the equation. Force over IL. Do we have force? Yes. 7 times 10 power negative 6. I, 7. L, 6. Magnetic field is equal to 1.7 times 10 power negative 7 Tesla. Z positive. How did you find the direction of the magnetic field? By using right hand rule. Question 2, it's very easy. This is length. Experiences a magnetic force. This is force. Magnetic force. Perpendicular uniform magnetic field. If the wire carries a current, this is current. Sorry, this is current. What is the magnetic field? Just replace, rearrange. FBIL, BF over IL. Question 3 is the same question. It's very easy. We have a length and current and force. You can find the magnetic field and just replace the numbers into the equation. You can get the magnetic field. Look at question 22 and question 31. We have two very good questions. A thin 1 meter long copper rod. So question 22. 1 meter long, L, 1 meter. Copper rod uniform magnetic field has a mass of the copper 50 gram. You have to convert to kilogram, 0.05 kilogram. When the rod carries a current 0.245 ampere, it floats, guys. It flows in the magnetic field. What do you mean by wire flows in the magnetic field? It means that the gravitational force of the wire that acts in Z negative downward is equal in magnitude with the magnetic force. When does the wire float? If both magnetic force and the gravitational force are equal. When net force is 0. If you remember in grade 10, you studied the buoyant force. When does an object suspend in water and when does an object float in the water? if the gravitational force of the object is equal to the buoyant force. If these two forces equal in magnitude but opposite in direction, the net force becomes 0. Okay? Gravitational force, guys, keep in your mind, always directed into the page, Z negative. Okay? So the wire, assume that the wire lays on the x-axis. Okay? So this is y-axis as x-axis, x positive, y positive. Okay? If you have a wire, we need shapes. Okay, so this is the wire and current carrying into this wire. The direction of the magnetic force, the direction of the gravitational force is always downward into the page, Z negative. Okay, so this is gravitational force directed to the Z negative. Okay, and so the direction of the magnetic force is in opposite direction of the gravitational force, magnetic force, Z positive. How many forces do we have, guys? 2 forces. What is the angle between these 2 forces? 180. Okay, these 2 forces equal in magnitude but opposite in direction? Yes, of course. So the net force becomes what? 0. The net force becomes what? 0. Okay, if net force is 0, which one is bigger? Same. Can we say that magnetic force is equal to Fg? Of course, why not? Fm is equal to Fg. Why? Because the copper rod floats in the magnetic field. Floats. What do you mean by float? It means that at balance. It means at balance. The wire does not moving downward and does not moving upward. Magnetic force is equal to what? BIL. Fg is equal to what? Mg. If you rearrange this equation, B is equal to what? B is equal to mg over IL. Replace m 0.05, g constant, I 0.245 times L is 1 meter. Magnetic field is equal to 2 Tesla. Is equal to what? 2 Tesla. In this way, you can determine the magnitude of the magnetic field when the copper rod flows into the magnetic field. The last question in this topic, question 31, look at this question. Very good question and very nice question. Be careful. The amount of current is 15 ampere. Directed along positive X. X is positive. The current is directed into the X positive, okay? This is the direction of the current. X is positive, okay? Perpendicular to the uniform magnetic field, the conductor experiences a magnetic force per unit length. What do you mean by magnetic force per unit length? It means that Fm over L. Fm over L is equal to what? 0.12 Newton per meter. Newton per what? Per meter. This is Fm over L. So instead, giving individual of magnetic force on L, both are given together. Fm over L is equal to 0.12 Newton meter. Okay, so we have to treat with this fraction as a one variable. This magnetic force is directed into the negative direction, negative y direction. The force negative y. If force is negative and current is on positive x, the direction of the magnetic field out of the page. The direction of the magnetic field B, Z positive. B is Z positive. So how can we determine the magnitude? We found it is direction. Now we have to find it is magnitude. Magnetic force is equal to what? B, I, L. Do we have L? No. We have to move into the denominator of the magnetic force, F, M over L. We can rearrange the equation according to math basic. B times what? I. Guys, look. Do we have Fm over L? Of course. 0.12. Do we have magnetic field? No. Do we have current? Yes. B is equal to what? 0.12 divided by 15. 8 times 10 power negative 3 Tesla. Okay? So in this way you can find and determine the magnitude and direction of the magnetic field. That's all for today, guys. Thank you for listening. Keep up your best doing. I hope you get benefited from my lesson. Inshallah, In the next lesson, I will explain the last topic in this section about the galvanometer. Thank you for listening.